Hello everyone. Now this is a little bit of bonus material, and following a request, I'm going to go over very quickly some ideas about what bonding is going on in alkenes. Now, in lots of cases, this is extension material versus your A levels. However, it does give a lot of understanding of what bonding is going on, and then that links into the chemistry. So it is important, and I'm hoping it does answer one of the great unasked questions in A-level chemistry. Okay. Right. Oops. Jumping on there. Okay, so what I'm going to try and go through is, this is in no particular order. I might be going through it in a slightly different order than this, but this is based on a task that everyone's been given. So explain what sp2 hybridization is, how it gives rise to the double bond in ethene, comparing sigma and pi bonds, really saying what they are, describing them in ethene, explain how the bonding affects the reactivity and why we get some geometrical isomerism. I'm not going to go into a lot of detail about that because that should be the subject of something completely different, and look at that separately. Right, so going to start off with looking at these types of bond. So sigma and pi orbitals, sigma and pi bonds. I'm going to sort of use the terms almost interchangeably, so please try and keep up, but they're essentially the same thing. So orbitals will overlap to form bonds, and the type of orbitals that are formed as a result of these are called molecular orbitals. Anyway, so sigma bonds, they lie on the internuclear axis. Let's get my pen out, here we go. So by the internuclear axis, what we mean is the axis between the nuclei of the two atoms that are involved in the bond. So, for example, don't want my pen. Okay, so hydrogen. So hydrogen, so let's imagine I've got my nucleus here and another nucleus there. I have two s orbitals, and these will overlap so that the result is I've got my nucleus there, Just pull up a pen. Green will do. So now, where the electron density is, because remember that's what's represented here, is on the whole going to be between those two nuclei. Okay, so this is a sigma orbital, okay, or a sigma bond. So the electron density lies between the axes. Now, example of pi bond. Okay, so these we're looking. I'm going to use ethene as my example here because that's what we're interested in. So in ethene, let's go to a pen I can see. So here, what happens? So I'm looking side on here. So that is my internuclear axis. So what happens is we then get electron density above and below the plane of the internuclear axis. Okay, now this is slightly different. You think, well, why is this a bond? Well, it is, and hopefully I'll go through some of that a little bit. So sigma bonds lie between the nuclei, pi bonds lie above and below that plane. Okay, so looked on the last page about how s orbitals can overlap. So that's my example was hydrogen in that case. So what we can also have is we can get sigma orbitals from p orbitals. Okay, so p orbital is an atomic orbital. A sigma and pi orbital is what we call a molecular orbital. So they exist when we're forming bonds. So when we've got a molecule being formed, then we get these molecular orbitals, which is why they've got subtly different names. Anyway, so I'm going to look at a carbon atom. Okay. We'll look later why this might not be the best example, but it'll give you an idea. So, in fact, I'm going to just look at this. So we know from when we did atomic orbitals, we have pi orbitals, and we have 3 of them. And they're 3-dimensionally arranged around the sort of the Cartesian axes. So that's going to go off into the background there. That's going to come in front of my screen. Okay, so that's where my p orbitals are. Now, looked on the last page about what can happen if p orbitals overlap above and below the plane to form a pi orbital. Well, if I have a p orbital on that axis there, and I have another carbon atom over here with a p orbital on that axis, we can see that these lobes can interact. So what forms from these, if these overlap, my atoms are going to come together. I'm going to get a region here of high electron density, and my lobes are going to stick out the other side there. So this electron density lies on this internuclear axis that I've drawn rather confusingly in the same colour. Okay, so we can get sigma orbitals formed from p orbitals. Okay, I'm only mentioning this just in case you get confused thinking S is always sigma or sigma is always S and P is always pi, pi is always P. There can be cases where they're not. All right, you go away. Next page, right, here we go. So, hybrid orbitals. So, think about methane, sort of the simplest hydrocarbon that we can come up with. And what we know about methane is that it's got 4 equivalent carbon-hydrogen bonds. And we know they're equivalent because they've got the same bond strength, perhaps. They've got the same reactivity. And we know it's the same bond angle, so they've always got to be the same. It's always 109.5 degrees, so it must be the same. But if we then look at this diagram here, that sort of backs that up. I put a but in the wrong place. So this is like a Lewis diagram, whatever you want to call it, dot cross diagram, showing that you get an electron from a carbon, electron from the hydrogen, they overlap. Everyone's sort of kind of happy. So these things here, just representing those sort of single bonds that we get between the carbon and hydrogen. But, this is where my but should have appeared. If we look at what the orbitals are, then we can sort of get a little bit confused. So if I just populate this diagram here, so I'm going to put 2 electrons in that 1s. I'm going to then move to what? 2s, I fill 2 in there, and then 1, 2. And that would be my atomic electron configuration for carbon. So how can I form 4 equivalent bonds out of all this lot here? So this is my valence shell. My s orbital is full, and then I've got 2 electrons in my 3p orbitals. So what on earth's going on? Well, this is when we get this hybridization thing going on. So what happens is our s orbitals and our 3p orbitals, they undergo hybridization. So what this means is they kind of blend together, and the result is, remember we're now forming a molecule out of all this. So carbon atoms, they are as they are on the left, but in a molecule these hybridize to be 4 identical orbitals, and then the electrons will spread themselves out, 1 into each. So if just delete these a second. Go away. Oops. So I'm going to keep my energy up here. So I've spread it out a little bit. So that's my 2s, and that's my 2p. Now what happens on hybridization, change my colour a little bit, is these will combine, and the energy level that we get is going to be somewhere between the two of them. It's going to be a blend or an average of those s orbitals and the p orbitals. So the s is lower in energy here. The p orbitals are higher in energy, so our hybridized orbitals are somewhere between them. Okay, you could probably say it's going to be, I don't know, 75% on the way up towards the p or something like that. So that is why we then have one electron in each of these. These are half filled, so then these singly occupied orbitals then can overlap with the s orbitals of the hydrogens. So where we've got to is our carbon now has these sp orbitals, which are a bit weird because they've got lobes and stuff on, and we've got 4 of them. Now each of these can then join up with the hydrogens, which have s orbitals, and we've formed 4 equivalent bonds. Excuse the diagram, it's a bit rubbish. So we call these, should have gone onto this page next really, so move across. Okay, so we call these sp3 orbitals. So going back to where I was, so I've got my 2s and my 2p's. So these hybrid orbitals that go to make up our bonds over here come from 1s and 3 p orbitals overlapping to form these new molecular orbitals, these sp3 hybridized molecular orbitals. Right. That's when I should put all my stuff. Right, so now, ethene. So now, this time, what we're going to look at is pi bonds only come from overlapping p orbitals, as far as we're concerned. So these occur in our carbons. And here I've got my diagram again, just to sort of help us. Now, one from each carbon is going to overlap. So this is diagram here just sort of shows a sort of a side-on view. So you might have seen these before. So the white ones here are my hydrogens, there's my carbon obviously, and we've got these bonds that occur between the nuclei of each of the atoms in there, the carbons, the hydrogens, and the carbon and the carbon. So these are sigma bonds that will form. But then we get this overlap of our p orbitals. So the blue represents the p orbitals, and they overlap to form the pi orbitals for the sort of what is going to be the double bond, okay, or the second part of the double bond. So over here I've mentioned that the double bond contains the sigma and pi bonds. So one of them, this one in the middle here, that's the sigma, and then our p orbitals overlap to form our pi bond, which is represented by that sort of green blob of space. Now, just to sort of go into this a little bit. So this time these are called sp2 orbitals. Okay, so they hybridize, so they're blended together to form sp2s. Now, one p orbital is used to make the pi bond, so that leaves us with 1, 2, 3 sigma bonds for each carbon in there. Okay, so those 3 sigma bonds need to come from somewhere. So get rid of that. It's not very sensitive today. So here we go, my diagram again. So one of these p orbitals, okay, so I'm just nominally saying that one, is going to be used to make the pi bond. So what's left behind to make our 3 sigma bonds is an S and then 2 P's. So it's an sp2 hybridized. And these orbitals that we now form are going to be somewhere. So here's my energy level. So I've got energy up there. So one, got one in there. Okay, so these are going to then go one, somewhere between the two, and one electron in each. And then these can then overlap with our hydrogens or with the other carbon. So this hybridization idea is how orbitals become lower in energy, and we get a stability associated with the bonding. That's the whole point of things, bonding, become more stable, lower in energy, which is another topic in itself, and if you really want to ask questions you can do. But what we're wanting to sort of look here is, okay, well, what does it mean when the carbons are sp2 hybridized? Well, it means it forms 3 sigma bonds, and it leaves one p orbital available to do pi bonding, which leads us on in a little while for explanations of reactivity. Okay, so here we go. So reactivity. So because our pi electrons, so these electrons in the pi bond, in the pi orbitals, sit above and below the plane, we can get regions of high electron density which can then attract electrophiles. So I'm just going to show an electrophile up there, E+. So electrophiles really love electrons. Yeah, that's why they're electrophiles. They love electrons. So these are going to be really attracted to the electrons here, but likewise the electrons there are going to be really attracted to the electrophiles. And when you start drawing your mechanisms for your electrophilic addition, for example, you're going to show the bonds, electrons in that region there going towards the electrophile. Okay. Because it's all to do with the fact that these are above and below the plane of the molecule, they're easily accessed. Okay, this electrophile isn't going to see much of these electrons in the middle there. Okay, it's not going to do any chemistry with that. It's sort of a lot more inaccessible. Whereas when it's in a pi orbital, it's a lot more accessible and more available for electrophiles to attack. Okay, so then we've got a little bit about isomerism. So in a normal bond, let's get my pen back up again. So what we have, so let's say I've got ethane. So I've got carbon, and then around this I've got hydrogens, they're like that. Hydrogens, so I'm showing us 3D of these. So these single bonds, these can rotate. Go red. So we can get rotation around these axes, and then it happens constantly. Okay, so these molecules are sort of spinning around, and if say it's not a hydrogen, it's a chlorine or something like that on there, and a chlorine on there, it doesn't matter because at some point this is rotating around, so they're always in the same position. Now with ethene, because this double bond is fixed, so it's between those p orbitals from each of those carbons, and they're in a particular orientation, they're like sort of holding it stuck. So now we don't get any rotation around there. So if these groups here are different, they're always going to be in the different position. So ethene, there's no isomerism, but if we moved on to something like butene, okay, or butene particularly, because butene won't, we get fixed rotation about the double bond, and because we've got different groups attached on either side of the double bond, then we can get EZ isomerism. And again, I'm not going to go into a lot of detail on this. You should perhaps have picked some of this up when you've done isomerism on these. I think you've done them, I'm not sure. But it's this idea here. So the double bond prevents rotation about the internuclear axis. And if you've got different groups attached to the carbons on either side of the double bond, then you can get EZ or geometric isomerism. Right. So, what have we done? We've explained what sp2 hybridization is and given rise to the double bond in ethene. So this is how one s orbital and two p orbitals kind of merge together. They become hybridized to form three sp2 hybrid molecular orbitals, which is why it forms three sigma bonds in ethene. That leaves behind one p orbital, which is available to form pi bonds with the other carbon, which gives us our double bond in ethene, which leads on to point 3. So this pi bond with the electrons lying above and below the plane of the molecule are more available for electrophiles to attack, therefore dictate some of the bonding in alkenes. Looked at sigma and pi bonds and described them in ethene. So sigma bonds are those ones that lie on the internuclear axis. Pi bonds lie above and below the plane of the internuclear axis. And why the double bond will give rise to geometrical isomerism in some alkenes but not ethene, and that's about having different groups attached to the carbons on either side of the double bond. You'll find plenty of information that on your textbook or on any other A-level chemistry stuff. Okay, I hope this was help. I wasn't quite sure what you were after, but any questions, let me know.